So we ended with coming up with a formula for this particular scenario where the area could be represented as n plus 1 over 2n. Before we relate this to limits, let's just double check our answer. So what if we had, I'm just going to say 6 rectangles because we did that. We would end up with 6 plus 1 on 2 times 6, which is 7/12, which is approximately 0.583, which is what we got. What did we get for 12? So 12 plus 1 is 13 on 2 times 12 is 24, which is approximately 0.542. I think I said in the previous one that was 0.541. So just check your rounding on that. I rounded wrong. Okay, so obviously our formula works because we're getting the same answer. And if we put in 100, you would get even closer to our answer. So I would have 100 plus 1, so 101, over 200, 2 times 100, which is equal to approximately 0.505. So we're getting closer and closer to our actual amount of 0.5. So what happens here when we try to relate this to limits, and yes, limits didn't go away, as n goes to infinity, so as the number of our rectangles approaches infinity, then the width of those rectangles, the change in x of our rectangles, which is 1 on n, is going to approach 0. So the more rectangles you try to shove under your curve, of course, the width is going to get narrower and narrower and narrow, so it's approaching 0. Then the sum of their areas is approaching the actual area of the region under the curve. Okay, so let's write that out. Then the sum of their areas, the sum of their areas is approaching the actual area, need more space, the actual area of the region under the curve. So in our particular example here, the area will be the limit as n goes to infinity of our function that we just made to represent the area, which was n plus 1 on 2n. And when we go to figure out this limit, we have to go back to chapter 1. And remember that if we're evaluating limits that go to infinity, we need to divide out by the highest exponent. In this case, we reduced it to an exponent of 1. So it's n on n plus 1 on n on 2n on n. And hopefully you remember, as n gets infinitely big, this guy's going to go to 0, so he goes away. And then I'm left with n on n, which is 1, and 2n on n. So I'm left with 1/2, which is the actual area that we calculated at the very beginning of our triangle, of our geometric shape. So the limit becomes the area under our curve. And so here is our beautiful formula. So the area is equal to the limit as n goes to infinity of the sum of the areas of each of the rectangles. And in this case, I is equal to some rectangle in the middle. Okay, some rectangle in the middle of the sequence. And we're going to watch the other part of her video here in just a sec. And she uses K. Okay, so in our case, the I is some rectangle in the middle of our sequence. Okay, the change in X is our width. So here's our width. And then Xi is equal to the left boundary A plus the width of some rectangle in the middle, whichever one it is that you're trying to find. This is really important, okay? So this is helps you to find your f of xi piece. And I don't think these are on formula sheets, okay? So this is important in helping you find your length or your height, okay? In our example, a was 0, so it was kind of irrelevant. We just had f of 2/5, f of 3/5, f of 4/5. But if a hadn't been 0, we would have had to add that in first. So if a had been 1, we would have had to gone 1 plus 2/5, 1 plus 3/5 to figure out where we were at for our x value in order to plug that into our function. Okay, so these are actually an intro to Riemann sums. If you wanted to learn more, there's a link here to Khan Academy. But before I get into an actual meat and potatoes example, we're going to go back and just finish up that example that she started and look at her intro to limits as well. So let me see if I can figure out where to press play. Here we go.
So there's really two parts going on here. If we look at the graphs as n gets larger, it looks like the area covered by our approximating rectangles is getting closer and closer to the actual area under the curve. If we look at our numerical data, it's actually telling us what these rectangular approximations are, and it's hinting that the area under the curve is approximately 1.3 repeated. So the last thing we want to do in this module is actually try and use formal limits to prove that the area under the curve is equal to 1.3 repeated, or 4/3. So for our final example, let's show that the rectangular approximations for f of x equals x squared plus 1 over the interval 0, 1 converge to the number 4/3. So we're just going to do it for one method. We're going to use the right endpoint method. So in our notation, what we want to show is that the limit as n goes to infinity of Rn, our nth rectangular approximation, is 4/3. It might not be clear how to even start this problem. First, seems like we're going to need a general formula for our nth approximation Rn. So really we want this approximation written down as a function of n. So let's start our process. We start by dividing the interval 0, 1 into n equal subintervals. The length of our interval is 1, so each subinterval has length 1/n. Let's label the important points on the x-axis as follows. Well, x0 is our left endpoint, which is 0. x1 is going to be 1/n to the right of x0, so x1 is equal to 1/n. And so on, we get x2 equal to 2/n, xk is equal to k/n, all the way down to xn, which is the right endpoint, which is equal to 1. So now these n intervals, x0, x1, x1, x2, all the way down to the nth interval, xn minus 1, xn, form the bases for the n rectangles in our approximation. So each rectangle will have base 1/n. The height of the particular rectangle is determined by the function value at the right endpoint of the interval. So for the area of the first rectangle, well, we use the right endpoint of the first interval, which is x1. So the height is f of x1, and of course the base is 1/n. So you can see the area of the first rectangle is the product of these two values. For the kth rectangle, we get the same formula, but now we're using xk, which is k/n. And for the nth rectangle, we're now using xn, which is 1. So now that we have a formula for the areas of our rectangles, we can add up all the areas and get a formula for Rn. So you see it here, we're adding up these n quantities we've already computed to get Rn. So now the game is just simplification. Can we get this into a form that we recognize so that we can take a limit as n goes to infinity? So each term has a common factor of 1/n, so we pull it out. And now we're left with f applied to a bunch of numbers. Well, remember that our function f is just x squared plus 1, so f of 1/n is 1/n squared plus 1, and so on down the line. So now doing some simplification, we're grouping like terms here. We group the n many ones together, and all of the squares together. So we can put the terms 1 squared, 2 squared, all the way to n squared over a common denominator of n squared. And finally, if we multiply through by the fraction 1 over n, we get the following result. So this was a pretty good start, but it's not clear what the limit of this expression is going to be. So to finish this off, we actually need to use a numerical fact that you may or may not be familiar with. You may be familiar with the formula due to Gauss for adding the integers from 1 to n. If we're trying to calculate 1 plus 2 all the way up to n, then we get the fraction n times n plus 1 over 2 as a function of n. Turns out that there's actually a similar formula if we'd like to add the squares of the integers, which is what's relevant to us in our expression. If we take the sum 1 squared plus 2 squared all the way down to n squared, we get a different fraction, n times n plus 1 times 2n plus 1 over 6. If we plug this formula into our expression for Rn, we get some nice simplification. We see that the factor of n in the numerator of this fraction cancels with one of the factors of n in n cubed in the denominator of the fraction. Multiplying out our remaining two binomials, we get the following expression. 2n squared plus 3n plus 1 all over 6n squared, and then plus 1. So now we have a formula for Rn, and we can start talking about the limit. But before we do that, let's just check that this makes sense. We already have a value for R5, which we computed earlier on. So let's plug in n equals 5 to this formula and see if we get our answer out. You can see if we plug in n equals 5, we get 1.44 out of our formula. And if you check back to our original approximation that we did by hand, we got exactly 1.44. You can check another one. If you plug in n equals 10, we get 1.385. Now the computer generated that for us. We didn't do it by hand, but notice that that matches the number we got for R10. This is one way of checking that our formula makes sense. Finally, we need to take the limit of our function Rn as n goes to infinity. So if we tackle the fraction in Rn, we see that as n gets large, the term 2n squared in the numerator will dominate the other two terms, and the term in the denominator, 6n squared, is alone. So when the limit as n goes to infinity, we get a ratio of 2 over 6, or 1 over 3. So finally, we can take the limit as n goes to infinity of Rn, and we get 1/3 plus 1, which is 4 over 3, which was our predicted value.
And that was that. Now we're going to try to do some of these. Okay? So notice how she was using the sigma notation sum formula. Let's go back here for a sec. She was using this formula right here. Okay, this is the one that she ended up using because she was adding up 1 squared plus 2 squared plus 3 squared plus ... n squared. Okay, so you can see how these are going to be really important so that we can simplify our expressions so that we can then evaluate the limit as n goes to infinity. Okay, so we are going to come back in the next video and see if we can come up with finding the area under y equals x squared from 0 to 2 as our boundaries using this numerical method and not using what we learned in 10.1 and 10.2. Of course, you could use that to check your answer at the end of this. Again, we're just doing these to learn the method, this numerical method with functions that are easier to work with. And this is kind of getting into Riemann sums, which is really important for university, I hear from first-year calc people. So I'll see you back in the next video.